everyone. Myself Dr. Sandeep Kumar, Assistant Professor, Ramjas College, Delhi University. Dear students, today we will discuss about the pyrrole as the heterocyclic compound. So in pyrrole, we are going to discuss the basic introduction of pyrrole molecule, thereafter structure and aromatic nature of pyrrole, then resonating structure of pyrrole, further its physical properties, and then we will discuss the synthesis of pyrrole. In the synthesis, we are going to discuss these different kind of synthesis like Pall-Knot synthesis, Hence pyrrole synthesis. We will also discuss the synthesis of pyrrole from furan and thereafter synthesis of pyrrole from succinic anhydride, then pyrrole synthesis, and at last we will discuss the synthesis of pyrrole from acetylene. Thereafter we will discuss the chemical properties of pyrrole. In chemical properties, we will discuss the electrophilic substitution reactions, and in electrophilic substitution reaction, we are going to discuss the different kind of electrophilic substitution reactions like halogenations, nitrations, sulfonation, Willersmeyer-Hack reaction, Gaiterman formylation, coupling reaction, Hoban-Hoch reaction, acylation reaction, and we will also discuss the basic character of pyrrole. Further, we will discuss the acidic character of pyrrole as well. Then, on the basis of acidic character of pyrrole, we will discuss the Kolb-Schmitt reaction, Rimmer-Timon reaction, reaction with alkyl halides, thereafter reduction of pyrrole, oxidation of pyrrole, reaction with malic anhydride, ring expansion reaction of pyrrole, and at last ring cleavage reaction of pyrrole. So in this way we will discuss the pyrrole in detail. So let's start with the basic introduction of pyrrole. So pyrrole is highly significant heterocyclic compound as its core structure is found in numerous natural substances such as alkaloids, chlorophyll, and hemoglobin. So additionally, it is also present in coal tar and bone oil. So you will see the structure of pyrrole on the screen that it's a 5-member heterocyclic compound with nitrogen as the heteroatom, and there is lone pair of electrons on the nitrogen atom. So it comes under the category of aromatic heterocyclic compound. So now we are going to prove the structure of pyrrole molecule and its aromatic nature. So the molecular formula of pyrrole is C4H5N, and considering the tetravalency of carbon and the valency of nitrogen, the structure of pyrrole can be represented like this. In the molecule, both carbon and nitrogen atoms are sp2 hybridized. So the electronic configuration of carbon can be written as 1 electron in s orbital and 1 electrons in each of the 3 p orbital. So 1 electron in 2px orbital, 1 electron in 2py orbital, and 1 electron in 2pz orbital. So since the carbon has sp2 hybridization, then there will be contribution of 1 s orbital and 2 p orbital. So the hybridization will be sp2. In similar way, the electronic configuration of nitrogen in the excited state will be like this. There will be 1 electron in 2s orbital, 1 electron in 2px orbital, and 1 electron in 2py orbital, and there are 2 electrons in 2pz orbital. So in this way the hybridization of nitrogen is sp2. So each carbon atom in the ring has 3 sp2 hybrid orbital as we have seen, and each containing 1 electrons and 1 unhybrid p orbital that is perpendicular to the plane of hybrid orbital, and that also hold a single electron in case of carbon atom. In similar way, the nitrogen atom is sp2 hybrid with 3 sp2 orbital and each containing 1 electrons and an unhybrid p orbital that is perpendicular to the plane and which holds a lone pair of electrons. So carbon atom utilize their sp2 orbital to form 3 sigma bonds. The 3 sigma bonds will be carbon-carbon bond, carbon-hydrogen bond and carbon-nitrogen bonds, while the nitrogen atom utilize its 3 sp2 orbital by forming 3 sigma bond. Out of 3, 2 will be Cn sigma bond and 1 will be NH sigma bond. So after forming these sigma bonds, each carbon has unhybrid p orbital with 1 electron and nitrogen has unhybrid p orbital that contain 2 electrons. So these 5 unhybrid p orbital, 1 from each carbon, there are 4 carbons, and 1 from nitrogen atom will overlap laterally to form a continuous and delocalized pi electron cloud above and below the ring. You will see in this figure that 4 carbon atoms and 1 nitrogen atom are forming a pi electron cloud above and below the plane of the ring. So this cyclic pi system having all 5 ring atoms and contains a total of 6 electrons. 4 electrons from each 4 carbon atoms and 2 electrons from nitrogen atom. In this way there are 6 electrons. So these 6 electrons known as aromatic sextet, and which is also responsible for the aromatic character of pyrrole molecule as per Huckel's rule, that is 4n plus 2 pi electron rule. So if any molecule is aromatic in nature, then the molecule will have resonating structure. So according to resonance theory, pyrrole can be represented as resonance hybrid of several canonical structures with an overall resonance energy of approximately 92 kilojoule per mole. So you will see these 5 resonating structures in case of pyrrole, and you will also see that there is positive charge on nitrogen atom and negative charge on each of the carbon atom. Means there is positive and negative charge separations involved in these resonating structures, and when there are positive and negative charge separations are there in the molecules, then the overall stability of that molecules decreased. So as a result, pyrrole has only one major contributing structure that is relatively more stable, because in that structure the molecule do not have any positive and negative charge separation. But in case of benzene, we know very well that there are 2 equally stable chiral structure that do not have any positive and negative charge separations. So this difference explains why the resonance energy of pyrrole is lower, that is 92 kilojoule per mole, than that of benzene, that is 151 kilojoule per mole, and that's why benzene is more aromatic than pyrrole. So now the physical properties of pyrrole. So pyrrole is a colorless liquid. It has boiling point 404 Kelvin. Further, pyrrole quickly turns into brown color when exposed to air. So further, it has a smell similar to that of chloroform. It is partially soluble in water but dissolve readily in organic solvents like alcohol and ethers. Now we will discuss the synthesis of pyrrole molecule. So in the synthesis we will discuss these 7 different syntheses like Pyrrole synthesis, hence pyrrole synthesis. We will discuss the synthesis of pyrrole from furan. It is also assumed as the green method. We will discuss in coming slides, and then synthesis of pyrrole from succinic anhydride. Thereafter, we will discuss the norpyrrole synthesis and further the synthesis of pyrrole from acetylene. So, the first synthesis, that is Pyrrole synthesis. So, in this method we do heating of 1,4-dicarbonyl compounds in presence of either ammonium carbonate or ammonia, or we can take primary amines or hydrazine as well. So, in this process there will be cyclization takes place and formation of pyrrole will take place. So, in this reaction you can see that we have taken hexane 2,5-dione, that is the example of 1,4-dicarbonyl compound. So, when this hexane 2,5-dione is heated in presence of ammonia or ammonium carbonate, then there will be elimination of 2 molecules of water will take place and we will get 2,5-dimethyl pyrrole as the product. The mechanism of the reaction can be understood that, as we know that the carbon of carbonyl group is electrophilic in nature, and ammonia, because of presence of lone pair on the nitrogen, act as the nucleobase. So, the nucleoside will attack on the electrophilic carbon of 1,4-dicarbonyl compound, and there will be formation of this intermediate. Then from this intermediate there will be elimination of water molecule and we will get this intermediate. In this intermediate there will be intramolecular attack on the electrophilic carbon of carbonyl group by the NH2 group. So, there will be intramolecular nucleophilic attack, and further after dehydration we will get 2,5-dimethyl pyrrole as the final product. The second synthesis is hence pyrrole synthesis. So, in this synthesis we do condensation reaction between alpha haloketones with beta ketoester and in presence of ammonia or primary amine. So, that results the formation of pyrrole derivative. So, in this process there will be elimination of water molecule as well as hydrochloric acid from the reaction mixture. So, the mechanism of this reaction will be, the reaction will take place in 2 steps. Step 1 will be the attack of ammonia on the electrophilic carbon of ethyl acetoacetate. So, after the attack, nucleophilic attack, there will be elimination of water molecule and we will get enamine as the intermediate. In the second step, this enamine will attack on the carbon of alpha chloroacetone and there will be elimination of hydrochloric acid and we will get this intermediate. So, thereafter in this intermediate there will be intramolecular nucleophilic attack will take place on the electrophilic carbon of carbonyl group and followed by dehydration will produce the pyrrole as the final product. The third synthesis of pyrrole molecule can be carried out by using furan. So pyrrole can be prepared by heating a mixture of furan and ammonia under the presence of alumina as the catalyst. So this is one of the greener method for the synthesis of pyrrole, because in this synthesis water will be the produce as the side product, and this method is also used for the commercial scale as well. The next synthesis of pyrrole is from succinic anhydride. So when succinic anhydride is treated with ammonia, it forms succinamide. So the enol form of succinamide upon reduction with zinc dust yield pyrrole. So you will see in this reaction that when succinic anhydride is treated with ammonia, then it will produce succinamide. So this molecule is succinamide, and it will tautomerize into enol form, and further on reduction with zinc dust we will get pyrrole as the final product. The next synthesis of pyrrole is nor-pyrrole synthesis. So in this synthesis the reaction between alpha aminoketones and carbonyl compounds that contain an active methylene group, that is an electron withdrawing group at the alpha position, to produce substituted pyrrole is known as nor-pyrrole synthesis. So we have alpha aminoketones and we also have ethyl acetoacetate. So when we do condensation reaction between these two molecules, then there will be elimination of water and we will get pyrrole derivative as the product. So thereafter we do reaction with aqueous solution of potassium hydroxide, which will hydrolyze the ester into acid. Further, on heating there will be elimination of carbon dioxide gas, that is decarboxylation will take place, and finally we will get 2,4-dimethyl pyrrole as the final product. So the mechanism of this reaction can be understood that the reaction involve attack of nitrogen on more electrophilic carbonyl carbon. So in this way you will see the attack of amine on the more electrophilic carbon of beta ketoester. So the reaction proceeds via the formation of enamine intermediate. So after the attack there will be elimination of water molecule and we will get enamine as the intermediate. So in this enamine there will be intramolecular attack by the enamine on the electrophilic carbon of carbonyl group. So we will get this intermediate, then at last there will be elimination of water molecule and followed by rearrangement of proton will produce pyrrole derivative, that is 2,4-dimethyl pyrrole molecule. The last synthesis of pyrrole molecule can be carried out by passing a mixture of acetylene and ammonia over red hot tube. So in this way we have to take two molecules of acetylene and that are heated in presence of ammonia, so they produce pyrrole as the final product. So now we will discuss the chemical properties of pyrrole molecule. So as we have proven that pyrrole is an aromatic compound, so the characteristic reactions of aromatic compounds are electrophilic substitution reaction. So pyrrole has significant aromatic character and that makes it highly reactive towards electrophilic substitution reaction. Nevertheless, it can also participate in addition reaction, which we will discuss in the coming slides. So these are some electrophilic substitution reaction that are shown by pyrrole. So pyrrole on reaction with nitrating agent will produce nitration product. In case of Pyrrole, the nitration will take place at 2 position, and similarly we can do sulfonation, acetylation, halogenation, and Willsmere-Hack reaction. So we can do many electrophilic substitution reactions that are possible on any aromatic compound. So let's start with electrophilic substitution reaction. So it is the observation that Pyrrole is more reactive than benzene in case of electrophilic substitution reaction. Why this is happening? Because the nitrogen in Pyrrole can donate its lone pair to the pi electron cloud. The electron density on its carbon atom is significantly higher than that in case of benzene. So as we know that Pyrrole is a 5-member heterocycle ring, and benzene is a 6-member ring. So both are 6 pi electron system. In case of Pyrrole, the 6 pi electron density is distributed over 5 atoms, but in case of benzene, the 6 pi electron density is distributed over 6 atoms. So in this way, in case of Pyrrole, each atom has more than 1 unit of electron density, because there are 5 atoms and the electron density is 6 pi electrons. But in case of benzene, there are 6 atoms and the electron density is also 6 pi electrons. So that's why each carbon has 1 unit of electron density. So as a result, Pyrrole is much more reactive than benzene and behave similarly to highly reactive benzene derivative like phenols and amines in electrophilic substitution reaction. So the orientation for the electrophilic substitution reaction in Pyrrole can be seen that the electrophilic attack will take place at 2 position rather than at 3rd position. But if the 2 position is already occupied, then the electrophilic substitution reaction will take place at 3rd position. Why this is happening? Because in case of electrophilic substitution reaction, the reaction take place in 3 steps. The step 1 is generation of electrophile, the step 2 is attack on electrophile, and the step 3 is removal of proton. So when there is attack on electrophile, that is step 2, that is the rate determining step for any kind of electrophilic substitution reaction. So in case of Pyrrole, when the attack will take place on the electrophile by 2nd carbon, then we will get highly stabilized intermediate and we will get 3 resonating stabilized intermediate. But in case of 3 position, when the attack take place at 3rd position, we get only 2 intermediate. That's why the electrophilic attack in case of Pyrrole is preferably take place at 2nd position. Thank you very much for watching this